From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. Let's see, we don't have a basketball game today, do we? So when's the next game? Saturday. And see, who is it we play on Saturday? ASU. Oh, okay. Well, let's get on to interferometry then, in that case. I had a couple of students come by with questions that made it obvious to me that I didn't explain something very well the other day. So let's go over it again here. And this is where we were looking at a plane parallel plate, fringes from that. We had a source up here, and I'm going to have an extended source here. I show it as a point, but it's really an extended source. Light comes down here, and I trace just one ray down. And this ray is such that inside the plate it makes an angle theta with respect to the normal. And the second beam comes up here, parallel to the first beam. And we said that we know that if you trace one ray through the system and you get two rays out and they're parallel, that the fringes will be localized at infinity. And so we just put in a lens and went in the focal plane to look at the fringes. Now the thing is, I've drawn only one ray here and one angle of theta. And so that one angle of theta is focused at this point here. If I came in with another angle here, so I had a different angle of theta, that would leave at a different angle, and that would be focused in a different position here. Okay? So we have light focused at a lot of different positions here, and for each position it corresponds to a particular theta. And if this condition, this is the phase difference between the two interfering beams. And if this is equal to an integer times 2 pi, we'll get a bright fringe. Integer plus a half times 2 pi, we get a dark fringe. And the fringes we get look like this. So this would, if I just take one of these fringes, that would correspond to a theta in one direction, and then we can go around a circle here. So this would correspond to a given OPD, a given theta, so we go around the circle. Next fringe out would be a different theta, and so on. So do you understand how this comes from? If we had only a point source, well, if we had ray coming in only at one angle anyway, we'd have only a single point here. But the fact that we have rays from a lot of different angles, and actually a lot of different points on the source, but a lot of different angles here means that we will have light spread over some area here, and depending upon the theta, the wavelength, thickness of the plate, refractive index of the plate will determine whether a particular theta gives a bright fringe or dark fringe or something in between. So now you're all experts for sure on a plane parallel plate. You'll see fringes of this sort coming up all the time. In fact, we'll soon talk about the Michelson two-beam interferometer. We're going to get a very similar result in that case. Shall we go on? No questions? Okay. Well, we just started this at end of last class. So this is section 6.3. And it's Michelson two-beam interferometer. And we're going to talk here about 6.3.1, extended source. And this will be what we call a division of amplitude interferometer. So for this, I don't have to sketch something. I will bring out one of the view graphs. And it's a pretty simple little interferometer. In fact, I guess you already have done a little bit of your homework with it. And it's something that every course in optics you take, you always cover the Michelson interferometer. It's dates way back 1881. And we start out here, and as I said, we'll have an extended source. We will go through here, and we have a beam splitter. And part of the light's going to be reflected up here to this mirror, comes back down. Part of the light will go through here, come back here, and out here. Now we put in this little thing called a compensator plate. Sometimes that's not present, but often it is, and the reason is the following. If we look, we trace this ray here. Let's say we're reflecting off a second surface there. So the light goes through the glass again, back through the glass again. Here, the light goes through the glass, and if I didn't have a compensator plate, it would just go here and back again. And so what we do, we put a plate in here, same thickness as this, same angle as this, same material, so you have the same dispersion as the beam splitter. And so both arms are going to see the same amount of glass. Now you might say that, why don't I just take this plate out and I'll just move this mirror to the right position to match the paths. And the thing is, you could match the optical paths for one wavelength that way, but because you have dispersion in the glass, you would match it so you have a different optical thickness for different wavelengths. You could, without this compensator, you'd only be able to match the paths for one wavelength. So we put the compensator in, and we're able now to match paths for all the wavelengths. Okay? If we use a monochromatic source here, we might just save our money and not have a compensator. White light source, wide bandpass source, you need a compensator. Now, there are a couple of different ways that we can set this up to look at fringes. And one way is we set it up such that for a single ray going in, the mirrors here are adjusted just right, so the two rays coming out would come out parallel to one another. So extended source, two rays here come out parallel. Where do we have to look for fringes? Where are the fringes localized? Up pretty close to where the ASU game is going to be, far away, infinity, okay? Okay. So when we look at these fringes, we're going to look at infinity. So what we're going to do to calculate what the fringes look like is that we're going to redraw this. We're going to unfold this. And if I look, put my eye here and I look back in there, I'm going to see a mirror, another mirror. Each mirror, the reflection off each mirror, I'll see a source. So I'll see two mirrors, I'll see two sources, and if one of these mirrors is a different distance from the beam splitter than the other one, the images of the mirrors and the images of the sources will be in different locations in space here. So we'll see something like what I have in the next view graph. This is now looking back into the instrument. I see two images of the mirrors, and I'm saying the mirrors were such that one path was a distance d longer than the other path. So I'll see two images of the mirrors separated distance d. If the mirrors are separated distance d, the images of the sources will be separated distance 2d. Okay? Now this is going to be an incoherent source, and so spatially incoherent. So light from each point will only interfere with light from the corresponding point in the other image of the source. So here I show one point, here I show the corresponding point in the other image. I trace the rays back parallel, and I say what path difference do I see in the light coming from here and the light coming from there. Well, this is separated distance 2d. I'm looking at an angle of theta, and so the path difference is 2d cosine theta. And we saw that last class when we looked at plane parallel plates. Very similar situation. So the OPTI is 2d cosine theta. If we, for the time being, neglect or forget about any phase changes on reflection from the beam splitter, then we would say we get a bright fringe when 2d cosine theta is equal to integer number of wavelengths. If we have a phase change on reflection, then maybe the fringes will be shifted. But that's a basic equation giving us the shape of the fringes. Because of symmetry, the fringes are going to be rotationally symmetric. And I mean, that's the same equation we saw last class. So we know what the fringes look like. They look a lot like this. Same old pattern again. Okay. So how many of you dreamed about this pattern last night? I don't know. What are you people dreaming about? You're not dreaming about the right stuff here. Okay. Any questions on that? How many of you have had the Michelson in classes before? Some of you will admit it, but not all of you. So. Okay. Well, let me ask you a question here. So these are the fringes we get. Let's say we set up this interferometer here, and let's say we reduce D. So the path difference becomes smaller, the two paths become more nearly equal. And so my question is, as we decrease D, will these fringes move out? Will they expand? Or will they contract? Let me write that down here. Decrease D, fringes expand or contract. Move out or move in. Maybe we should vote on that. Let's decide this by the democratic process. Okay. Unfortunately, I can't take the votes from the people out in TV land, but I'll take them from here. How many say it expands? 1, 2, 3, 4. 4.5? Oh, 4. Okay. 4 expand. Contract. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4 plus 9 is 13. I guess the rest of you is saying the fringes don't even move? Is that the answer? Let's see. I don't know what they do. Let's see here. We have this equation that you're dreaming about. 2d cosine theta is m lambda. For a given fringe, m is some number. If d decreases, theta must, and for a given fringe, this is a constant, so if d increases, cosine theta must what? Increase. And so theta does what? Decreases. Oh, democratic process worked. They do contract. They do move in. Okay? So as we reduce d, the fringes are going to come in. The fringes will shrink. Okay? Any questions on that? See how, other than voting, you see how we decided how to do it? How it worked? Okay. Well, these are fringes of equal angle, Heidegger fringes. There's another way that we can get fringes here, and that is, let me go back to that drawing. What we're going to do now is to take this, and instead of moving it in and out, we're going to tip this a little bit. Okay? And so now the two beams coming out here will come out at different angles. And so this is going to be called fringes of equal thickness. So this is 6.3.2. Fringes of equal thickness. Okay? So now if we tip this a little bit, so the rays are coming out at a different angle, for one ray going in, the two corresponding rays are coming out at a different angle. The fringes are going to be localized, wherever these two rays intersect. So our drawing might look something like this. So here we're looking back in two mirrors. In this case I have them separated just a little bit, but I have them tipped. And so we have one point here, and the rays are coming out at different angles. They intersect back here, and so that's going to be where the fringes are localized. And that will turn out, as long as the separation between the two mirrors is pretty small, this will turn out to be very close to where the mirrors are. And so they're localized in this region right here. And the fringes will be more or less straight. They're fringes of equal thickness. So we have the separation here, so there will be fringes. If the tip is like this, the fringes would go perpendicular to the paper here. And they would be such that in going from one fringe to the next fringe, the OPD changes by a wavelength, and so it would be essentially that the separation here would change by half a wavelength in going from one fringe to the next fringe. So here's some more pictures here. And I stole this out of someone's book. And I think it's Jenkins and White. I'd like to give them credit, but I'm not 100% sure that's what it was. I stole it a long time ago. So we have two situations here. We have fringes of equal angle, and I guess this doesn't show up too well on the overhead, but on the TV. Fringes of equal angle, and then fringes of equal thickness. Let's just look at the top ones first. So here's where the paths are matched. D is equal to 0, and we have one fringe. And it may be a bright fringe, or it may be a dark fringe, depending upon the phase change on reflection. And in fact, I might go back here just for a second, if I can find it. We'll come back to this. Let's go back here, and let's say these two mirrors are the same. Same reflectivity, so whatever phase change on reflection I get here, I get the same there. Light goes in, reflects from inside to outside. Light comes here, reflects from outside to inside. If these paths are matched exactly, will the fringe I see be bright or dark? Or do we have to vote again? Any brave person will volunteer? You have a 50-50 chance here. Better than a lot of things in life. Bright. Sorry.
Dark.
Ah, there, that's very good. Why? No idea. Okay, let's see if we can figure that out then. High index to low index to high index. Remember a phase change on reflection? And this is, say, a dielectric. Or maybe I didn't say that. That's why he said, right. This is a dielectric here. And so there will be one of these will be phase shifted 180 degrees relative to the other one. And so when the paths are matched, there's a 180 degree phase change on reflection, and so it's a dark fringe. Okay? So we're going to have one big dark fringe. And that's what we have here. Now I'm worried about something. We have all this light going in, and we get one big dark fringe here. Where has the light gone? Any other brave person who would volunteer here? No? Well, let's see, light can go here, here, and out, but it all can go here and zip back there. Here, out, but it can go here and zip back towards the source. So no light coming out here, the light is going back towards the source. So if we have a dielectric beam splitter here, this pattern coming out here and the light going back towards the source will be complements of one another. And you know, here we have it goes a high index to low, reflection, low to high, so the two beams 180 degrees out of phase. But if we look at light going back to the source, this guy is, he's never reflected. This guy's reflected once, reflected again, and so if it's 0 first time, it will be 0 the second time, but if it's 180 the first time, it'll be 180 the second time, or 360. And so the paths are matched, these two will be in phase. Okay, so we have this is dark now. Now as we increase the separation between the mirrors, we get fringes. And the greater the separation, the closer together the fringes are. 2d cosine theta m lambda, okay? So these are fringes of equal angle. Now we tilt one of the mirrors, and we get fringes that look like this. And the fringes here, well, when the mirrors are, when the paths are very closely to being matched, and maybe it's matched for the center fringe here, we're going to get essentially straight, equally spaced fringes. Fringes of equal thickness. But now as we increase the separation here, so for the first case, these two mirrors probably overlapped someplace here. Now we increase the separation, and the fringes look a little curved. I don't know if you can see that on the TV. Yeah, I guess you can still see these fringes. They're a little curved. These are curved this way, and these are curved this way. Okay, so as we, in one direction, one mirror is closer than the other, and the other direction, the other mirror is closer. So one question might be, why are these guys a little curved? And why are they curved the direction they are? Well, physically, you can think why they're curved is that if I were to trace the distance here, look at the light from a single point, it will be, if these mirrors are separated, it will be a different distance for the light to go from the point to one mirror to the eye and the point to the other mirror to the eye. And so we have a longitudinal shift between the points, a different curvature for the two beams, and so we get slightly curved fringes. If a curvature is the same, but it's just an angle between the two beams, we get straight, equally spaced fringes. Curvature is different, we get curvature difference and no tilt, we get circular fringes. Curvature difference and we have some tilt, and we'll get essentially straight fringes, but they'll have some curvature to them. And that's what we have here. And the question is, why are these curved this way and these are curved this way? Yes,
One of the beams having a curvature different than the other?
Okay, the question is, why does one beam have a curvature different from the other? Light, let's just take light from one point here, trace it here. You know, for one mirror, the light goes here, here. For the other mirror, and so it appears to be coming from some point back here. For the other mirror, it goes here and here, appears to be coming from a point back there. So if I look back here and the two images of this point, they appear to be different distances away. Okay. Now, why are these curved this way and these are curved this way? Remember, for this one, One case, this is M1 and this is M2 like so, and then we've moved so it's the other way. So the direction of the wedge would be the opposite direction. And so if we think here for a second, OPD is 2d cosine theta. As I'm looking, theta is 0, say right in the center here. As I look up here, theta increases. Or if I go down here, theta increases. So theta increases, cosine theta decreases, so for a given fringe, d must increase. So theta increases, cosine theta decreases, d must increase for a given fringe. Okay. So as we move up here, this fringe is moving towards the portion of the wedge that is thicker, d increasing. And so this is actually convex towards the thin side of the wedge. The wedge being the angle here between these two rays. So is all that confusing enough? Simple little interferometer, but there's a lot to it. But I tell you, once you understand this guy, the rest of the interferometers just, they just have different names, only different. Okay.
Instead of curved.
Flat being one fringe?
Being straight.
Straight. Straight is, you're going to have the best straight fringes where the mirrors are tilted relative to one another, and there's some point where the path difference is equal to 0. And then I'm going to get these straight fringes here. So straight fringes just come from beams interfering at an angle. Curved fringes come from beams having different radius of curvature. So we like to have these two. If I look back and see the mirrors, when the best situation for straight fringes is where the two mirrors intersect. There's one point here where the paths are matched, and then we're going to get straight fringes here. As the separation changes from one fringe to the next fringe, the separation changes by half a wavelength. And that actually takes us to our very next topic here, which is white light fringes. Okay. So what we're going to do now is that we're going to tilt the mirrors to get fringes of equal thickness. And we know, because of coherence, if we have a wide spectral bandwidth, we're going to get good contrast fringes only when the paths are matched. So if I go to this situation, so these are the two mirrors, I'm going to get best contrast fringes right here. And as I move out, the fringes for the different wavelengths will get out of step, and the fringe contrast will drop off. So I have a little picture here. Which again is in your view graphs. And I've done this for a case where we have the 180-degree phase change on reflection. And so when the paths are matched, the fringes fall right on top of one another. In this case, I get a dark fringe because of 180-degree phase change on reflection. Now, as we move out here, we're going to get fringes. And we're going to get fringes every time the path difference changes by a wavelength. And so if we have short wavelength blue light, we're going to get fringes closer together than what we get for the red light. And so they're right in phase here, but as we move out, they're going to tend to get out of phase. And so as we go out here far enough, the fringe contrast is going to go away because all the different colors are out of phase with respect to one another. Okay. And if we just think here for a second, let's say we have two wavelengths present. And let's say that the center fringe is dark. So just two wavelengths instead of white light for simplicity. Say center fringe dark. And so OPD is, I wrote here, m plus a half times lambda for the max. And OPD, say m lambda for the min. That's true because the center fringe is dark. And so if we have two wavelengths, when do the fringes get out of step? So when does the max for one wavelength fall at the min of the other wavelength? You've kind of done this in your homework, but we'll write it down anyway. That's going to be when m plus a half, say lambda 1, is m lambda 2. So one of these is a max for one wavelength, and it's a min for the next wavelength. And we solve this for m. That will be lambda 1 divided by 2, lambda 2 minus lambda 1. So the OPD, m lambda 2, will be lambda 1, lambda 2 divided by 2, lambda 2 minus lambda 1, something we've seen a few times before. This will be the optical path difference that causes these two sets of fringes to go out of step. We have a maxima for one falling at the minima of the other one with this optical path difference. Okay. Any questions? So these white light fringes are really very useful. And I'll write this down, that white light fringes are useful for detection when arms of an interferometer are equal. And I've found, this is one of the most useful things that I've ever found in my life, I'd have to say. This is for work that we did out at Waco, this was a very essential part of the product line. Very simple concept, known by Michelson back in the 1800s, but certainly very, very useful. Okay, any questions? Now you had a question on the homework, part C of question X, I forget which question it was. But the question was something about, can we look at circular fringes, fringes of equal angle, or do we have to look at equal thickness fringes? Remember the question? You remember the answer? Okay. Let's see if we can figure it out. The whole idea behind it was that we had a certain spectral width of the source, and so the path difference, in order to get good contrast fringes, the path difference had to be pretty small. And I don't remember what the number was. Does anyone here remember? I don't have the homework problem answer sheet with me. A few microns, I think, probably, wasn't it? In any case, D could be very small in order to get fringes. And so if we write down here that OPD is 2d cosine theta, okay? D is small. On axis, OPD is 2d, theta is 0. So the question was, let's say this is some number m1 lambda, and this is some number m2 lambda, and these may or may not be integers, doesn't make any difference. But in going from on-axis to off-axis, we would have that 2d times 1 minus cosine theta is m1 minus m2 lambda. And for reasonable values of theta, and I don't know what you want to put in, I think in my solution sheet I use 20 degrees, but maybe you want to use 30 or 40, I don't know. But the point was that d was so small that for all reasonable values of theta, delta m is small. And so the number of fringes, number of circular fringes we would see would be small. And I think I had going out to 20 degrees, we only had like half a fringe or something change from axis to off axis. So this is not, circular fringes, fringes of equal angle, is not a good way of looking at fringes when the path difference has to be small. A much better way is to go to fringes of equal thickness. And if you go to like white light fringes, you always look for white light fringes with fringes of equal thickness, because there's a point that I can make the OPD equal to 0. Here, if I want to have more than one fringe, the only way to make the OPD equal to 0 would be to let theta go to 90 degrees, which is not too practical. So for large bandwidth, short coherence length, you look at fringes of equal thickness. Okay? So you all feel like you're experts on the Michelson two-beam interferometer? It's a pretty useful, pretty neat little interferometer described in all books that cover interference talk about the Michelson interferometer. Most labs where you do any lab experiments at all in interferometry, the Michelson is one of the first ones you would do. It's a very fundamental interferometer, very useful. Ready to go on? We'll celebrate and I'll have a little medicine. Okay. Section 6.4. This is called the Twyman-Green. We don't have any French students as French people as students do. For some reason the French they will not call this a Twyman-Green. They still call this the Michelson. And you'll see why in a minute. This Twyman and Green got a patent on this in 1916. And I'll show a picture of it. And I will show a laser as a source, but I guess in 1916 they didn't use a laser as a light source. But what they did here, boy, it looks a lot like a Michelson, doesn't it? The only difference here is that in the Twyman-Green, we use a point source. In this case, maybe it's a point source in infinity, so it's a collimated beam. But all the Twyman-Green is a Michelson, where we use a point source instead of extended source. I'll write that down here. Like Michelson, except point source instead of extended source. Okay. Now this is widely used in optical shops, optical testing, testing of flat mirrors, curved mirrors, lenses, prisms, corner cubes, everything, diffraction gratings. So another commercial for optics 513 next semester in optical testing. We'll spend a lot of time talking about the Twyman-Green at 8 a.m. Haven't been able to get it changed to 7 yet. Working on it. Okay, 6.5. Mach-Zehnder interferometer. Picture again. I show this, I'm going to show it using a laser as a light source, but you don't have to use a laser as a light source. Mach-Zehnder, source, beam splitter, light goes this way, light goes this way. A couple of mirrors, another beam splitter, light goes out here, light goes out here. Here we have fringes. Okay. And typically you'll put a sample in one of the arms and you're checking the transmission properties of that sample. Okay. Laser, point source, collimated beam, maybe I should say. Where are the fringes localized?
Finished.
No. The non-localized. Point source, the fringes exist every place. The two beams overlap. So the non-localized fringes. Normally what we will do here was put the lens in, we'll image the sample here, but the fringes are every place with a point source. Back in the olden days when they didn't have a laser, and to get a fair amount of light, they couldn't use a point source, so they used an extended source. So now the fringes would be localized someplace. And you'd like to get the fringes localized in the same plane as the sample, because you'd like to image the sample here. So you want to see the sample and see the fringes at the same time. So if we had an extended source here, so the fringes are localized, you'd want to tip and tilt beam splitter and mirror such that, for a given ray going in, you have two rays coming out, and you wanted those two rays to be intersecting back where the sample was. So you could always, tip and tilt and translate and stuff to get fringes localized in the plane of the sample. With a laser, you don't worry about that because they're non-localized. Okay, any questions? No questions? I have to ask you a question then. I set this up, perfect optics, perfect sample. And I adjust the paths here, phase changes on reflection and stuff, so I have a bright fringe coming out here. Well, no, let's say we have a dark fringe coming out here. No. Say we dark fringe here, one big black fringe. Where has the light gone? All this light going in, nothing coming out here. Where's it gone? George, you're right. It goes up here. I mean, we show light coming here and here, but also you have light going up here and up here. Okay. So light goes up here. If these are all dielectric coatings or beam splitters here, then you can show that the two beams here are out of phase by 180 degrees. So whenever you have a bright fringe here, you're going to have a dark fringe up there. Now let's just say you go out and you just buy some beam splitters and you don't, you're not real careful about whether the dielectric coatings or not. You put this together and you end up with no light here. I mean, you get a black fringe here. And you say, oh, the light must be up there. But I look up here and I can come up with a situation where there's no light here and no light there. Where has the light gone in that case? It's a trickier question. Thought I almost heard an answer.
Going back,
What?
back to the laser.
No, how would it can't get back to the laser in this case. Twyman-Green it does, or Michelson it gets back to the laser, but here it can't. Well, here what the problem is that we definitely have put in some beam splitters that have metallic coatings that have absorption. And you can have a situation where you have no light here, no light there, and all the light is being absorbed by the coatings on the gratings. Okay. So you have to, when I try to figure out where all the light is, I look at all the outputs here, and then also have to add up any absorption that I might have in the system. Okay, well that's the Mach-Zehnder. Section 6.6. Lateral shear. There are a million different lateral shear interferometers, and everyone seems to have one named after himself. Here's one that's very common, and all it is a plate, but it works pretty nicely for describing what we mean by lateral shear. So here I show a collimated beam coming in. Some of the light's reflected off the front surface of this plate. Some of the light is transmitted through and is reflected off a second surface. It comes out. So I have these two beams coming out that are shifted sideways with respect to each other, i.e. there's a lateral shear between the two beams. And in the region of overlap here, we will get some interference fringes. And it will turn out, and again in Optics 513 we study this a lot, and I'll show a little bit more in another view graph, but if this turns out to be spherical waves, these fringes will be essentially straight and equally spaced. If we have other aberrations present, then fringes will have a different shape. But we just have a lateral shear between the two interfering beams. In this case, the shear is delta x. Okay. So this is called a plane parallel plate interferometer. It's a shearing interferometer, but in this case it's a plane parallel plate. Now, whenever I see this, I'm reminded once I published a paper where part of the paper I had this interferometer in it, and I got a letter from a person called M.V.R.K. Murdy, and he told me that this is called a Murdy interferometer. So I just want to make sure that everyone knows that. Okay. This is a Murdy interferometer. Okay. And he had published it back in the early 60s, I guess, or something. Anyway. Well, let's think a little bit more about lateral shear fringes. And what we think, we have some wave front coming along here. And let's say that wave front is delta W of x and y. And we're going to interfere that wave front, whatever it is, with a shifted version of itself. So I just wrote that as delta W of x. Delta W of x plus delta x and y. And we're going to get a bright fringe whenever this difference here is equal to an integer number of wavelengths. Forgetting about phase changes on a reflection, that may shift the fringes. And I can kind of rewrite this as the partial of delta W with respect to x averaged over the shear distance times delta x, the shear. And so the point I'm trying to make here is that a lateral shear interferometer measures the slope of the wavefront. And to be a little more precise, it measures the average slope, average value of the slope over the shear distance. Okay. Have any of you used an interferometer like this in the lab? And what purpose did you use it for, other than the past lab course? Right, measure collimation of the beam. And this turns out to be a very, very convenient way of measuring collimation of a laser beam. You have to have reasonable coherence length because the paths are certainly mismatched. One beam goes through the plate twice and the other beam doesn't. So if you have long enough coherence length, you can use this to test for collimation. And I thought I'd show a view graph on that. And again, those of you, if you take Optics 513, you'll hear more about this than you want to. But I'll just mention it here because it's so useful. That let's say we take the first case where we have really the plane parallel plate, the Murdy version here. If the beams are collimated, so you have plane waves, over the overlap region, you're going to have one fringe. Maybe bright, maybe dark, I don't know. But you can show here, and we're not going to do it in this course, but you can show that if I depart from being collimated, I have slightly spherical, then I'm going to have these straight, equally spaced fringes. And maybe you can just close your eyes and kind of see why that's true, that we have two beams that are separated in space, and they're going to be essentially straight, not perfect, but essentially straight, equally spaced fringes we'll get. And so you simply would adjust the collimation here to get one fringe over the field of view. Now, there's actually a little better way of doing it. A little better way is we will make this plate where the two surfaces are not parallel to one another, but we'll have a little wedge. And if we have shear in this direction, I'm going to put wedge in the opposite direction. Not much, a few seconds of wedge in the opposite direction. And so now we will get, when the beam is collimated, we're going to get fringes like this due to the wedge in the plate. And when we go away from collimation, we tend to get fringes like this, and so what that's going to do is to rotate the orientation of the fringes. And so we will have, if the shear is this way, the wedge is this way, when it's collimated, the fringes will be like this. Away from collimated, the fringes will rotate. And so you'll adjust this to get, you adjust collimation to get horizontal fringes in this case. And I think there's a little mistake in those of you who got the handout on this. And I think I show in the handout a different number of fringes here than here. And that's not correct. There should be the same numbers, just that they have rotated. So that's a lateral shear interferometer. And that's all we're going to say about it in this course. We have one more section here. And this is 6.7. And this is going to be called radial shear. And for that, I will again go to the view graphs. And again, I show a laser as a light source, but it doesn't have to be a laser. What we have is we start off with an interferometer that looks, for this example anyway, looks a lot like a Mach-Zehnder. But in one arm I put a telescope in that made the beam smaller. The other arm I put in a telescope that made the beam larger. And so we have two beams coming out of here. A big beam and a small beam. Big beam, small beam. And in the region of overlap, we'll have interference fringes. And this is a radial shear. So, this point on one beam will correspond to that point on the other beam. So we have radial shear interferometer. And that's all I'm going to say about it, I guess. Any questions? So this chapter 6, was on classical interferometers, and we went through maybe 7 different types of interferometers, just kind of understanding the basics. I think, go back to the real fundamental, the plate interferometer we had, and the Michelson interferometer. If you really understand those two, in fact, if you just understand the Michelson by itself, you really understand most of interferometry, I would say. Any question? Most of two-beam interferometry, anyway. Any questions? Okay. If not, we can go on to chapter 7. Any notes? So we've talked about two-beam interference. There are many instances where we end up with more than two beams being present, and so we would get what we will call multiple beam interference, and that's what chapter 7 is. Multiple beam interference. And again, a lot of good references on this. Certainly the Heck's book, Born and Wolf, and a million other ones. This is covered in a lot of different textbooks. 7.1 is what we're going to call Airy's formula. A-I-R-Y. How many of you have gone through multiple beam interference in other courses? Okay, a few people. One person admits it anyway. It's covered in most beginning courses, I think, in interferometry anyway. And I gave you a couple of handouts today, and those of you out in TV land, sorry you don't have the handouts yet, but they're in the mail, I guess. But they're pretty simple. But I'm finding it easier to draw them back in my office, and probably neater to draw them in the office on the computer than to try to draw them here. So all we have is a plate, okay? Thickness D, refractive index N, outside of the plate index N prime, and I'm going to pick the same index up above as down below. And later, in probably about the next few graphs or so, we're going to say that there are no losses in this system, no absorption, no scattering, and probably next Tuesday or so we'll look at the case where we do have some losses. But right now, for today, there are no losses in the system. We illuminate this with a beam of light coming in at some angle theta prime. And so inside the plate, it will make an angle theta. We have some light reflected up here. Some light is going to go through, be transmitted here. Some light is reflected here and will come out here. And some will come down here and come down here. And we've already looked at the case where we interfered these two beams or we interfered these two beams. But what we want to do now is not just to account for these two beams, but especially if we have a higher reflectivity here, we'll have other beams reflecting back and forth. And we're going to get many beams coming out. both in reflection and in transmission. And in fact, we'll soon take the limit that the number of beams in reflection or in transmission is infinite. Okay? Now, we know that from previous work here, we know that if we look at two consecutive beams in reflection or in transmission, that the phase difference, neglecting any phase changes on reflection, the phase difference goes as 2 pi over lambda 2 nd cosine theta. So 4 pi over lambda nd cosine theta. N being the index inside here, d being this, and theta being the angle inside. And we take into account the refractive index n there. So this is lambda in vacuum. Lambda naught here in vacuum. Now, for our problem here, we're going to say that the light reflected from outside to inside here is little r. And little r may have some phase associated with it as well as an amplitude. But that's the reflection, little r. And if we reflect from inside to outside, the reflection is r prime. And again, there may be a phase change on reflection, I don't know right now, but it will be taken into account in the phase of r or r prime. Likewise, light transmitted from outside to inside, the amplitude transmission will be little t. And from inside to outside, the amplitude transmission will be little t prime. Okay? So if now I want to look at the reflected beam, and we'll look at the amplitude of the reflected beam, light comes in here, and let's say, I didn't say it, but say this is unity right here. What will be reflected up here is r. Okay? So the first beam is r. The second beam, well, let's see, what do we get? This beam goes through here, so we get t through. We get r prime reflected up here, and we get t prime through there. So it's t prime, r prime, and the phase relative to here, due to the optical path, will just be e to the I delta. Okay? So this is this guy. Second one here is this guy. Third one, well, let's see, what happens to this guy? So it's a t, r prime, r prime, r prime, t prime. So we get t prime, r prime cubed. And then we get e to the 2I delta. Okay? And so you can just keep adding all these up until finally you get out here to a term that's going to go as t prime, r prime to the 2p minus 3 it will turn out to be. So p is 1, p is 2, and so on. And then e to the I, p minus 1 delta. So p is 2, that's just 1 delta. Okay, so we're going to add up all these terms coming out here. So that will take care of the reflected beam. Now for the transmitted beam, let's see, it goes through here. We get t through, and then t prime. So that's the first guy, t prime. Second guy will be t, r prime, t prime. So t prime, r prime squared, e to the I delta. Next guy, well, we get a t, r prime, r prime, r prime, r prime, t prime. So t prime, r prime to the 4th, e to the 2I delta, and so on, till we get the beam number p. That would be t prime, r prime to the 2p minus 1, e to the I, p minus 1 delta. Okay? So we will add all these up. in a minute or two. Well, let's worry a little bit about these r's and r primes and t's and t primes. And so what we're going to say now is we have no losses in the system. And this will take us to this view graph here. So we have no losses, and then a wave propagation must be reversible. So what in the world do I mean by that? Well, let's say we have a beam coming in here of unit amplitude. We get an amount r reflected here. This is just one interface, okay. An amount t transmitted. Now let's turn the light around in the opposite direction. So I turn this around in the opposite direction, opposite direction. So I had r coming back. I guess I didn't show that here. But r coming back, t going back. What comes down here then will be t times r prime, because we're reflecting from this side to that side, plus r times t. So tr prime plus rt would be going in this direction. And coming back here, we have t coming back, and when it goes through here, we get t prime going in this direction. So that would be tt prime. We get r coming back. Sorry, I didn't write an r there. We have r coming back, reflecting off here another r, so that's r squared. So going back in this direction, we have tt prime plus r squared. So we had 1 going in. We have t prime plus r squared coming out, so t prime plus r squared must be equal to 1. You can see that. Down here we have tr prime plus rt, but there is no light down here. So that must be equal to 0. And so we solve here the first one. We get that t prime is 1 minus r squared, little r squared. And from the second guy here, we have r is equal to minus r prime. So that's saying, second guy is saying, whatever reflectivity we have going this way, from outside to inside, is 180 degrees out of phase with whatever reflectivity we have from inside to outside. That's something we have known for a dielectric, if that's the case. Okay. And so I can define little r squared as capital R, tt prime is capital T, that's equal to 1. Tt prime is 1 minus r, so that's equal to t. And capital R is little r squared, and once we square it, it's also equal to r prime squared. So these are what's called the Stokes relations. And we will make use of this when we do this huge summation here in a minute or so. Okay. Any questions? Very good medicine here. Okay. So basically what we're going to do here now, it's a little messy, but it'll work out pretty nice. We're going to add up all these reflected beams and all these transmitted beams and see what we get. And we're going to get something here that is absolutely remarkable. And in fact, next class, when we get through this, I'm going to show you what I think is the most amazing thing in optics. Okay? So adding up all these things right here, so when we look at this, well, I guess maybe I have to rewrite this, so we have to do a little work here. We don't have too much time, but we can get started on this. And so we can say that the reflected beam amplitude is equal to r plus t prime r prime e to the I delta times 1 plus r prime squared e to the I delta plus so on out to r prime 2 p minus 2 e to the I p minus 2 delta times whatever is incident, and let's say what's incident is 1. So all we've done is that we have factored this common term here out of all these other terms. And we look at this, and that looks like a geometrical series. And so this is equal to r plus t prime, r prime, e to the I delta times. Remember how you solve a geometrical series? Remember you multiply this by what the multiplication term is for each consecutive term. And then you form a new series that has one higher term in it. And then you subtract these two. And so you get 1 minus whatever the next term is, r prime 2 p minus 1, e to the I p minus 1 delta. So that's 1 minus the next term divided by, I forget, what do you divide by? 1 minus whatever the multiplication was. R prime squared e to the I delta. Well, so that's our result. But it's not quite the form that we normally let it be in. The next thing we normally do in our minute and 22 seconds that we have left, let's say that we're going to let the number of terms, number of beams go to infinity. So let P go to infinity. And so now the reflectivity becomes R. First guy doesn't change here. And we let P go to infinity. R prime is a little bit less than 1. So when we let that go to infinity, that becomes 0. And so we're going to get a TT prime. R e to the I delta, and then downstairs we're going to get 1 minus r squared, r prime squared e to the I delta. And I think at this point I have to stop because I'm almost out of time. So we'll come back and work with this on the next class. And this became a minus sign, maybe I should say, because I replaced r prime with r here. So I will see you bright and early next Tuesday morning, and we'll see a very amazing thing next class.
From the University of Arizona Distance Learning Program, this is Optical Sciences 505, Diffraction and Interferometry, with Dr. James Wyant. This broadcast is authorized by the Arizona Board of Regents on behalf of the University of Arizona. Any reproduction or retransmission of this course or use of same for granting of credit without the express written consent of the University of Arizona is strictly prohibited.
Well, I'll say good morning to everyone. I want to start out by reminding you that Thursday of next week, February 26th, see what happens that day. Does anyone know? Exam. Okay. Who do we play in basketball that day? What? Stanford? That's scary. Maybe it's lucky that you're getting the exam. I'm not sure, is that right? Anyway, if we do play Stanford that day, you may be lucky that you're getting the exam before the game and not after the game. Of course, I'll be grading it after the game, I guess. Right? Also, I'm sure everyone has been wondering, when is the final exam? And for those of you who can't sleep nights because you're worried about that, it's on May 14th, 8 a.m. Okay. Well, last class we were talking about multiple beam interference. And I have some notes I'm handing out over here on my left. And if you haven't picked them up, maybe you should. Yes, Okay, question 26, part D. C. Okay, refresh my memory. Oh, is that the one where we have a spherical surface on top of a flat surface? And initially they're touching in the center. And the question maybe was a little confusing. I had so many students stop in to see me because I call these things mirrors, but they're partially transmitting mirrors. And so it really was like a Newton's rings experiment. That's what the problem was supposed to be. So we have circular fringes, and the